Okay, good afternoon, everyone. We're going to go over the next t-test, which is for repeated measure designs. And then we don't meet next week. The following week, we go over another t-test, the last t-test, which will be two independent measure design. So give me a few minutes, or a minute or so to pull up the slides, PowerPoints, so we can start. All right. So this is part B of the PowerPoint number 5, which is chapter 7, hypothesis testing applied to means, and we're talking about the t-test. So we're going to do the second part, this one right here. Okay. All right. All right. We said that last time. We said there are 3 different t-tests, and we use these t-tests when the population mean and the standard deviations are not known, or they are unknown. Like if they are known, like we know, for example, if we use standardized tests such as IQ, we know what the population mean and the standard deviation for IQ is 100, right? And standard deviation is 15. So we use z-score. But what if we use some other test that is not a standardized? Then we use t-test. There are 3 different types of t-tests, like we mentioned last time. We talked about single sample, which you have one sample from one population, also known as a student t-test. Tonight, we're going to go over related samples t-test, also known as repeated measure experimental or aka design, or aka within subject designs, or paired sample t-test. Once again, we use one sample from one population. So what's the difference between 1 and 2? We repeat the measurements. For example, if you want to do pre-test, post-test, same population, but you pre-test and post-test. You measure twice. You measure your participants twice. Or before and after something, like pharmaceutical companies use this kind of t-test for their research before they take the medicine and after client take the medicine or patients take the medicine. It's a repeated measure design. If there are more than 2 groups, then we use ANOVA for repeated measure design. And we talk more about that in advanced statistics. Next time, about 2 weeks from now, we'll go over 2 independent sample t-tests. But for now, let's just go over related sample. Related sample t-test or repeated measure experiment, aka within subject design, also paired sample t-test. We use one sample from one population. Also used in causal or comparative research. How do we do it? A single sample of individual is measured more than once on the same dependent variable. The same subjects are used in all the treatment conditions, as mentioned before and after. Test, post-test. So in order to do our hypothesis testing, same way that we did the single sample t-test. Repeated measure experiment or related paired sample t-test. If non-directional or two-tailed test, then the researcher or alternative hypothesis, H1 or HA, would say that mu D or mean difference, there will be a mean difference. That means the mean difference is not going to be zero. Like the first measurement before was the mean was 90. The second time will not be 90 because 90 minus 90 is zero. No difference. But we think there will be difference in our research. But again, null on top, H naught, it says mean difference is zero. So null is out there, an entity telling us that you're wasting your time. There will be no difference before and after your measurement. Or if it's the drugs, the medicine, they say it has no effect. For example, if a group of patients have a high blood pressure and a pharmacist wanted to test a new medication to lower their blood pressure, no says it's not going to lower their blood pressure because, again, we got to do the measurement twice, before they take the medications and after, like 3 months, once they start taking the medication for like 3 months or so. No, so, before and after, it will be zero. The difference between before and after. Same as psychology, if we try a new therapy, Noel says, let's say depression test. Noel says, well, the difference will be zero. That means if you have a sample of depressed patients and you test them, and let's say their score will be, let's say, the average score for our group before you start doing your psychotherapy will be, let's say, 19. Well, after therapy, after 3 months of therapy, Noel says will be the same. 19 minus 19 is zero. But we think will be lower, will be much lower. So there'll be a difference. So that's what it's all about. We test the hypothesis. It's always the same. We say there is a difference, some kind of changes. Noel says no. Those are the symbol. If we're doing a two-tailed test or non-directional, if you're doing one-tailed test, then as you can see, H1 is us, the researcher. If we say increase, mean difference will increase. Then Noel says no, it'll decrease or even Steven. So if we say again at the bottom, mean difference will be less, Noel says no, it'll be more or even Steven. Step 2, once again, we'll go on page 702 or your stats book and look for critical value. And with that, you need to know what alpha is and what type of hypothesis you're using. one tail or two tail, directional or non-directional. You look for the value, critical value of t. The same way that we did it for single sample t-test. These are all the formula we're going to use tonight. And I'll compare the formulas for repeated measure design with the single measure at the left side of the screen. As you can see that they pretty much alike, except instead of m minus mu, you see a d. That d means difference. For single sample, you have one sample. So the x are your score. For this type of t-test, repeated measure or related measure, you have two set of scores, before and after, pre-test, post-test. As you can see, some data on the right side of the screen that we're going to go over shortly. You can see that x1 are the first time, let's say, whatever, before or, pre-test, and then basically testing people twice for whatever reason. And then x2 is the second time. But D, we need to know the D. That D means difference. The third column, the difference between x2 and x1. Keep in mind the formula on top, right side of the screen, right under the CV, critical values, page 702, it says D is equal x2 minus x1. So always subtract x2 from x1. And when you use the SPSS, put your x2 column first, then x1. I wrote them like this because your book has it like that, manually. Usually one goes before two. But for SPSS, you do the 2 and 1. So D is the difference between, let's say, 6 and 9, or 9 minus 6 is 3. The difference between 9 and 8, or 9 minus 8, is 1. We also need to have a D square. Those are the columns that we're going to be using. So you simply square the D. Square the 3 will be 9, 1 will be 1, 3 will be 9, 4 will be 16. So at the bottom of those columns, sum of D will be 27, and sum of D square will be 99. We need those two because we need to calculate the SS by using these D and D square. Because again, in the past with single sample t-test, we only had one set of samples. We had X, like if you look at the formula, how to calculate the SS for the single sample, it was sum of X square right about the green line. Sum of X square minus square the sum of X divided by N. So for tonight, repeated measure, we have SS is equal, instead of X, we have D square. And instead of X square, we have D square. So sum of D square, you plug it in, and instead of sum of D, sum of X, you have sum of D. Square the sum of D divided by N. And this is how you calculate the SS, and you plug it in that formula on top. You can see that the formula to calculate the T is, again, mean difference minus sample mean difference minus population mean difference. If you notice, I have a kind of pink or orange X over the sum of D. That means that value is 0 according to Knoll. Knoll says the difference will be 0. So you don't even have to write it down. So on numerator, all you have is sum of D. Is MD, sorry, is MD. and denominator is estimated standard error of mean difference, MD, mean difference, SMD. How do you calculate MD? Sum of D divided by N. So we have the sum of D is 27 divided by N. N are number of participants. Or, you can see that each person has two sets of scores and N is 9. There are 9 sets. So 27 divided by 9 is 3. And then again, as you can see, you need to know how to calculate estimated standard error for the single score, and then for the repeated, you have a D. That's estimated standard score of mean difference. And two ways to do it: either square root of variance over N or a standard deviation divided by square root of N. From the previous chapter, we talked about how to calculate the variance, which is SS over DF, and the standard deviation is just the square root of variance. In terms of calculating the effect size, pretty much the same way. Mean difference. In the past, for single sample, we had M minus mu. Now we just have MD, mean difference. And the denominator is same, S. R squared is same way that we calculated before, and DF is N minus 1 the same way, because we have one sample. Take away 1 from it. In terms of distribution, at bottom right side of the screen, there is normal distribution or bell shape, and you draw that with the 0 as a mean and 1 as a standard deviation for the T and the Z. And we're going to go over it in a second. So all the formula you need is right there for this quiz and this chapter, right in the middle. But here I also have them done this way, so you can take a look. It's clear, maybe. DF is the same thing. All of these are there from the past. How to calculate the standard deviation, variance, and SS in the past. But now, as you can see, the one is highlighted in yellow and the words are in green. That's the new way to calculate the SS. That's the definition. Sum of D squared minus the square of sum of D divided by N. So again, we went over all these. We talked about them from the previous chapter. They are the same here. Like here, R squared, percentage of variance accounted for by the treatment. It's similar to Cohn's death, also known as omega squared or omega squared. So we talked about this. You can always go back and look at the previous presentation if you don't remember. It's just like Cohn's D. It tells us once we calculate, once we reject the null as a researcher, it tells us that what percentage of variance accounted for that research. Like the higher, the better, just like Cohn's D. Like if it's 70 or 0.7, as you can look at the formula, you're going to come out with less than 1. The value will be less than 1, like 0.7, 0.8. So you got to multiply that by 100 to give it meaning. Let's say if it's 0.7, that would be 70%. So that means when you reject a null, 70% of those facts are related to what you're measuring. and the other 30% are factors that we're not measuring. Okay, and that number, if it's less than 0.01, that means not significant, no effect. If it's about 0.01 but less than 0.09, it has a small effect. If it's about 0.09 but less than 0.25, has a medium effect, and if it's 0.25 or greater, it has a large effect size. That means we can reject the null. It gives power to our research. So these are the formula that we just talked about, and we're going to go over the problem right now, research problem. Just 1 second, please. Okay. Research indicates that the color red increases men's attraction to women. According to these researchers, in the original study, men were shown women's photographs presented on either white or red background. Photographs presented on red were rated significantly more attractive than the same photographs mounted on white. So that's the research was done with those by Elliott and Niesta in 2008. So let's see, we wanted to test this hypothesis and find out for ourselves if it's true. In a similar study, a researcher prepared a set of 30 women's photographs with 15 mounted on a white background and 15 mounted on red. One picture is identified as a test photograph and appears twice in its set, once on white, once on red. Each male participant, so we had 9 male participants. Each male participant looks through the entire set of photographs and rated the attractiveness of the woman on a 12-point scale. The data in the next slide summarizes the responses for a sample of 9 men. We set the little significant 0.01 and we used non-directional or two-tailed hypothesis. So we wanted to know if the data indicates the color red increases men's attraction to women. This is our hypothesis. This is what we're going to test. Here's our data. You're going to see right there 9 men. We call them Mr. A, B, C, D, all the way. And the second column is their score on a scale of 1 to 12 to the pictures with the white background. And the third column, X2, is their scores, same people, same man, on pictures with the picture of woman with the red background. So as you can see, Mr. A right there, on a white background, he gave 6, on a red gave 9. Mr. B gave 8 and 9, and C 7 and 10, and so on. Your fourth column is D. D is the difference that you can see on top. 1 second. Between X2 minus X1. So let's say 9 minus 6 is 3, 9 minus 8 is 1. So those are the value of D, the difference. You add them up, so sum of D is 27. And then you square your D's. So 3 square is 9. Square of 1 is 1, and square of 3 is 9. You add up your d squared, sum of d squared is 99. We need those to calculate SS. And then again, that MD, sum of D divided by N, we already talked about that. Sum of D is 27, N is 9 participants, 9 men. 27 divided by N, 9 is 3. So value MD is 3. And then it said, note that in SPSS, enter X2 value first, then enter the X1. That's important when you do that. Otherwise, you come out with a negative number or different numbers. So in repeated measure design t-test, we have 2 treatment, but 1 group. We test them twice, but it's the same group. And again, DF is n-1. Okay, SS, those are the formula, and we already went over all that. Let's test our hypothesis, and then we go over that slide. Once again, Noel, we're saying there will be the difference between the second and the third testing for each person are different. Like if Mr. A score, let's say 6 for the person in white, is for the second, the person in red, he's going to give the same number, 6, but it is not so. It was 9. So we said, yeah, the mean difference is not going to be 0. So Noel would say, no, the mean difference will be 0. That means they give the same score to the picture of woman with a red background and a white background. No difference. Anyway, we need to go back to 702, page 702, to look for critical value. Just like what we did last time, we need to know first column, DF, which is n-2. So our n sample is 9, first column. Let me make this larger. So 9, if you look at the 9, and then we use two-tailed test, and then we said to use alpha of 0.01, I already underlined it. Okay, so DF is n-1. N is 9, DF is 8. n-1, 9 minus 1 is 8. So DF is 8, and you go all the way, look at that where it says two-tailed test or non-directional, and right there under 0.01, that's your alpha, it's 3.355. Remember that number. We're going to use it momentarily. So with that in mind, we calculate our T, whatever the value is. If that value is in the blue or shaded area, blue shaded area, then we reject. If it falls short, we retain. So let's do it. This is the formula, and you know the story now. You can see the data are on the top right side of the story. It says right side of the screen, and all the data. We're going to test our hypothesis, and right there, that pink dot, it says step 1. Noel says no difference, but we know that. We as a researcher know better, because there are differences between the score on the white background and the red background. So H1, the researcher, alternative hypothesis, says mean difference is not going to be 0. Noel says 0. Step 2, we need to find out the critical value of T. We already did that, and we draw our T distributions, and with the df is n minus 1, which is 8, and then alpha 0.01. We found out the critical value start at 3.355. So since it's two-tailed, we cover both tails at 3.355. As you can see right there, bottom right side of the screen. Because we don't know whether our calculated T is going to be positive or negative. So our cutoff point starts with positive or negative 3.355 right there. That's our step 2. Step 3 is calculate the T. Calculate the T, use that formula right there in the middle of screen. T is MD divided by estimated standard of mean difference. So because we said sum of D is 0, that value is 0. I wrote it down so you know it's really mean difference, sample mean difference minus population mean difference. But note says that's 0 population mean difference, which in this case, the difference between X2 and X1. Okay. So MD, we already calculated, is 27 over 9. Sum of D divided by N is 3. So that's numerator. We need to calculate estimated standard error, and 2 ways to calculate it, just like the single sample t-test that we described, which is a square root of variance over N, or S divided by square root of N. So how do we calculate the variance? Variance is SS over DF, so this means we need to calculate the SS. SS, right above that green formula, is sum of D squared minus square sum of D divided by N. As you can see, sum of D squared is 27, and sorry, sum of D squared is 99. And sum of D is 27. Square the sum of D, and then D is 27. You square it, is 81. And then, so sum of D squared is 99. 81 divided by 9, which is 79 minus 81 is 19. Let me see. It's 18. This is 18. Let me just make this larger. Yeah. So SS is 18. We want to know what is variance. 18 right there in the middle of the screen. 18 divided by DF. SS divided by DF is 18 divided by 8 is 2.25. That's our variance. So we wanted to calculate the estimated standard error of mean difference. The square root of variance, which is 225. The square root of 2.25 divided by N, which is 9 participants. 225 divided by 9 is 0.25, and the square root of that is 0.5. So we put that 0.5 is the denominator of that T formula. So numerator 3, denominator 0.5. So our T value, our calculated T, is 6. Step 4 is make a decision. As you can see, that 6 is positive. So we we're going to land right there, deep in the shaded area on the right tail of the t-test, in that shaded area in the rejection zone, which is rejection zone. So what's our decision? To reject the null. So we reject the null. Says that no, make no difference if women were red or white, but we reject the null, and according to our test, shows that yes, color, there's something about color red that makes the woman more attractive. So let's do the same thing now with SPSS. You open your SPSS, and at bottom left, click on variable view. You start with X2, and then type in X1. Then you click on data view and put the values of X2 in that column and X1 in the next column. Then you go to analyze. Same thing we did just like last time, and compare means. Last time we used one sample t-test. This time we use pair sample t-test. You got to know all the names, like repeated sample t-test or pair sample t-test. Same thing. Repeated measure design. So you click on that, and this is what you see. You need to move your variables, which are in your column 1 and 2, X to X1, from the left to the right. One at a time, just drag and paste them. Or just click on them and click on that blue arrow and transfer to the right side. Once you move them, because all those numbers are attached to those two words, X1 and X2. Once you've done that, then click on, let me make this larger. Okay, it's better. Then click on option, and then you'll see that by default, alpha is, by default, is 95%. Critical confidence interval is 95%. So alpha is 5% by default. So you change the confidence interval to 99%. This will make your alpha 1% or 0.01, because the text suggested use alpha 0.01. Then you click continue, and then click OK. And this is your output. As you can see, calculate the mean for X2, mean for the X1, calculate the standard error on top. And so, there's 9 people. And at the bottom, once again, if I give you this for the midterm or final, and I'll say, what's the alpha here? You look at right there, that circle, not thin one, which it says 99%. So confidence interval. The fact that 99% the confidence interval, we know alpha is 1% or 0.01 in proportion. That's how you tell what the alpha is. Now, if I ask you, did we reject or retain the null or fail to reject? Well, you look right there when it says significant. It's always the same, right? Significant, two-tailed, and then it's two-tailed. So write that number underneath of that thick circle. That is called p-value. That's probability value. If that number right there, I wrote it in red, if that value, if the p-value is less than alpha, then we reject the null. P-value is 0. Alpha is 0.01. Yes, it's less than alpha p-value. So we reject the null according to this. There's another example that you can look over it. It's similar in your PowerPoints. And then keep in mind, we also going to cover non-parametric tests. We said that for each parametric test that we cover, there is a substitute non-parametric test, because if we use the parametric test, we have to meet certain assumptions. We talked about that in the previous session. One of them is, for example, sample size. In this research, we had a sample size of 9. In reality, that's not enough to conduct a non-parametric test. I mean, a parametric test. It's not enough, because for parametric tests, you should have at least 30 participants for each group. So something like that, I would say 60. 30 the most, I mean, minimum 30. So with that in mind, we had only 9. So let's say if you were in some kind of place, like some hospital somewhere, a small classroom, doctoral classes, and you want to do some kind of testing, but you have only 9 participants. Can you use this test? No. But you need to know what's the substitute t-test for this repeated measure design. It's called Wilcoxon sign rank test or Wilcoxon test. It does the same thing. The only difference is that parametric tests are more accurate and they use mean for the average, but non-parametric use median. So try to use parametric tests. That should be your first option. But if you have to use non-parametric tests, then you use the right one. Like in this case, you can see this table. We talked about this last time. Last time we talked about single sample t-test, and then we went over the non-parametric substitute for it, which was sign test. Tonight we're going to go over Wilcoxon test, which is substitute for matched pair or pair t-test. And then again, next time, about a couple of weeks, we're going to go over that Mann-Whitney U-test. We talk about it then. So let's do it. You go back to your data or any data. You got to have 2 sets of data, before and after, just like that. And then these are different data, I know. But how do we do a Wilcoxon test? Same way we did the sign test last time for the single sample t-test, except instead of sign test, you click on Wilcoxon test. So you have your data, you got to have 2 sets of data for before and after, and then so you write them as after and before, just like x2 and x1, right? Instead of x1, x2, you put x2, x1. Anyway, we go to analyze, non-parametric test, legacy dialog, and then a paired sample. 2 paired sample. Then you move same way, you drag and paste your variable from left to the right. Same way we just described. And keep in mind, for non-parametric test, SPSS by default used only alpha of 0.05 two-tail. So we can't change that. Know that for non-parametrics, alpha is 0.05. So we look at the slideshow. Let me make it larger. Right there where I shaded in black, it says, once again, look where it says asymptotic significant. Two-tail. That's by default. It's 0.017. So that is our p-value. If our p-value less than alpha, we reject. So 0.01 is less than 0.05. Therefore, we reject. So if I give you this for final, so what's your decision here? You should know that if p-value, where it says significant, asymptotic means very small, close to zero, is 0.017. If that number, that's p-value, probability, is less than alpha, alpha is 0.05, then it's significant. Then we reject the null, and we did. So let's go over, some of these problems. Keep in mind, if you do these problems and email them to me, you get credit for it. Extra credit for the, for the final. So first one says, what's the value of MD, mean difference, for the following set of differences score? The formula for MD was sum of D divided by N. So we know N is 4. There are 5 sets of scores. MD is sum of D divided by N. So sum of D, these are D scores, okay? Difference score, D score, that's what the D is. You got 3 negative, that is -9, and -2 is 11, and 3, 14. -14 and positive 9 would be 5. 5, -5. -5 divided by N, which is 5. So that would be -1. It's that simple. Next one, like we said, what's the value of estimated standard error for the following D score? With this one, you need to calculate the variance, use the SS. Once again, you need to do like sum of D square. You add them up. 8 and to 10, 16 is sum of D, right? And then square each one of them and add them up will be sum of D square. That gives you value of SS. Once you got that, then you calculate the variance. Variance is SS over DF. DF is 5, N is 5, DF is 4. So that value divided by 4 gives you the variance. So estimated standard error is the square root of variance divided by N, which is 5. What's the value of estimated standard error? Now this one, number 3, you have everything. Estimated standard error is you got an SS already calculated for you, so you need to know the variance. Variance is SS over DF. 72 divided by 15. That gives you the value for the variance. And estimated standard error is square root of variance over n. N is 16. And let me know if you have any problem with any of these these problems. Just let me know, just copy it, send it to me, and I explain it to you. A repeated measure experiment with a sample of n is 20 subject would produce t-stat df of what? So df is n minus 1. That's no brainer, really. 20 minus 1 is 19. So do the rest, and there's 3 more. They're pretty much the same. And then, again, about 2 weeks from now, we go over the last t-test. We sum them up, and we get ready for ANOVA, analysis of variance, which is really, it's the just larger t-test for repeated measure. Like this one, if you do ANOVA, you have more than, you do your measurement more than twice. That's it. That's that repeated measure design, ANOVA. And again, for independent t-test, we have 2 groups, but for ANOVA, you have more than 2. And we'll talk about that when we get there. So please make sure that you look over the 2 independent t-tests, and which is PowerPoint number 6, and your textbook. Do your SPSS assignments, stay on top of that, and make sure you take your quiz. Other than that, once again, let me know if you have any question, concern about anything. Have a great day, and we'll talk to you next time. Mm-hmm. Mm-hmm.